You ever get that feeling that computers, they just don't seem to be getting faster in that same mind-blowing way they used to? I mean, for decades, we were in this golden age where every new computer felt like a giant leap forward. And then it felt like almost overnight, all that incredible progress just slammed into a wall. So today, we're going to dig into exactly why that happened and how a huge crisis in engineering actually sparked a revolution in how we compute.
All right, let's get right into it. To really get what happened, you first have to appreciate just how wild this era of growth was. Seriously, it set this expectation for computing power that, honestly, we all just started to take for granted. This timeline right here, it tells the whole story. Starting back in 1986, we were on this 16-year-long rocket ride. I mean, just try to imagine your computer getting a whopping 50% faster every single year. It was this incredible, predictable engine of progress. But then, right around 2002, that rocket ship didn't just slow down. It felt like it hit a solid brick wall. And to put that into perspective, look at this. The rate of improvement was more than cut in half, just plummeting from 50% a year down to only 20%. Now, this wasn't some minor dip in the market. No, this was a fundamental shift that sent shockwaves through the entire tech industry, and it raised one massive question. What on earth happened? Well, it turns out the answer wasn't about a lack of good ideas or money or anything like that. It was about physics. The very laws of nature, they became the biggest roadblock computer engineers had ever faced. So what we're looking at here is this unavoidable chain reaction. For years, the recipe for making computers faster was pretty simple. Make the transistors, those microscopic little switches inside a processor, make them smaller and pack more of them onto a chip. But here's the catch. Smaller, faster transistors need way more power, and more power creates a ton of heat. Eventually, they just got too hot. The chips would become unstable, they'd be unreliable, they could literally melt themselves. They had hit a thermal wall. With engineers totally stuck, they needed a completely new way of thinking. The old way was officially a dead end. But the solution they came up with was a genuine aha moment. And it's the reason the device you're watching this on right now still feels incredibly fast. So here's the big pivot. The whole strategy had to change. Instead of trying to build one single super fast brain that did everything, the industry completely changed direction. They decided to build a team of several, slightly slower, but much more power-efficient brains to work together on the very same problem. And in the tech world, each one of these brains is called a core. A core is basically its own little central processing unit, or CPU. So when you hear about a dual-core or quad-core chip, it just means there are 2 or 4 of these little processor brains working together on that single piece of silicon. And this image shows you that idea perfectly. You see that little square? That's a processor die. Instead of trying to make that one square impossibly fast and hot, the new design just put 2 or 4 or even more of them right next to each other. This right here was the birth of the multicore processor. But, this hardware revolution, it wasn't some kind of magic fix. While it solved the heat problem for the engineers, it basically just handed a brand new, massive challenge over to the software programmers. After all, having more brains doesn't really help if they don't know how to work together. You see, for decades, pretty much all software was written serially. Think of it like a single to-do list for one core to just work its way through from top to bottom. But running a serial program on a multi-core chip, well, it's like having one person trying to drive 4 cars at once. It just doesn't work. To get any kind of speed up, software had to be completely rewritten to work in parallel. This means breaking big problems into smaller chunks that all the cores can work on at the same time. And that is way harder than it sounds. Suddenly, you have to worry about complex stuff like synchronization, making sure all the cores work in the right order, and load balancing to make sure one core isn't doing all the heavy lifting while the others just sit around. And this wasn't a simple fix. As computer scientist Peter Pacheco pointed out, you couldn't just tweak the old code. Programmers had to fundamentally rethink how they solved problems, right from the ground up, designing entirely new algorithms that were built for teamwork from the start. So, why? Why go through all this trouble? Why completely re-architect both our hardware and our software? Well, because this new way of computing, this idea of parallel computing, it unlocks the power to solve problems we could never, ever have tackled before. Think about something as massive as climate modeling. Trying to simulate our entire planet's complex climate and weather systems, That's an unbelievably complicated task. It requires the kind of computational horsepower that only thousands of cores all working in parallel can possibly provide.
We can also use this incredible power to simulate the very building blocks of life itself. Understanding how proteins fold is absolutely key to fighting devastating diseases like Alzheimer's and Parkinson's. It's a puzzle so complex it's been called one of the grand challenges of modern biology. This also has a huge impact on discovering new drugs. By simulating how thousands of potential new medicines might interact with the human body, all at the same time, parallel computing dramatically slashes the time it takes to find new cures and get life-saving treatments to the people who need them. And it's right at the heart of our search for a sustainable future. Whether it's designing more efficient wind turbines, modeling fusion reactors, or discovering new materials for solar panels, all of these incredibly complex simulations depend on the power of parallel processing. So, you see, the great processor slowdown wasn't really an end, it was a crucial turning point. The big takeaway here is that a hard physical limit, that thermal wall, it forced the entire tech industry to pivot. They went from making one brain faster to using many brains working together. And yes, that created a massive software challenge, forcing programmers to learn a whole new way to think and code in parallel. But the result? We now have the computational power to tackle humanity's grandest challenges. And it really makes you wonder, with this incredible power at our fingertips, what impossible problem are we going to solve next?